Okay, so today we are going to be talking about section 3.2, which is derivatives of exponential and log functions. So we have a little background, a little reminder, some review, and then we're going to jump right into the new stuff and how to use this, how to do it all. Okay, so the first couple slides here, I'm going to go over them briefly. I'm not really going to go all in depth because I know it's not necessary for all of you, but of course you're always more than welcome to slow this down or download the slides and play it yourselves. But it's going to sort of derive and talk about where all of these definitions come in. Okay, so in this particular case, we're going to be talking about derivatives of e to the x, this function right here. Very important. Okay, so if you remember, e to the x, is about 2.7. So it's an exponential function. The base is 2.7 is e, and it's again kind of fitting in with everything we've done before, where it's the natural number. It works in anything in nature and in kind of growth or decay, this e is involved. So this is basically what the function is. And if you ever want to get kind of a graph of it here, it sort of looks like any other exponential function. Okay, about like that. But there's a couple unique traits to this which makes things work out nicely. So what they're going to do is they're going to find the derivative of what e to the x is. So if you remember, we have all of this stuff over here, and they're going to break it down. Like I said, I don't expect you to know this and to be able to derive it. There's only one part that matters, and it's this final conclusion right here, this e to the x. Okay, now all of this, after all is said and done, here's basically what it's saying is, if you were to take the derivative of e to the x, it is e to the x. It's the easiest derivative out there. Notice it doesn't follow the power rule. The power rule is when you have a function where there's a power and the x is the base. This is the case where the x is up in the power, right here. When you get that, it has a whole set of special rules. This is just the beginning. But if you are given e to the x and you're told to find the derivative of that, it's a very simple answer. The derivative of e to the x is simply e to the x. It's the exact same thing. Now, as you get different powers, you start getting numbers or things up there with the x, then the rules are going to change a little bit, but it's going to fit the same basic structure that anytime you take the derivative of e to the x, it is simply going to be e to the x. And that's all you really have to know out of all this. Like I said, these slides are kind of giving you the definition, but that's all that matters right there. Okay? Now, a couple little notes here talking about be careful when you're using your calculator. Make sure you're using the correct e function right there. And this other one's important here. Notice it doesn't work like the power rule. Okay, so if I'm finding the derivative of x to the third, remember the rule was we bring the power up front and then we drop the power down by 2. That's when the power is a number. A plus, minus, negative, fraction, anything. But when your x is up in the power, it's a whole different game. Okay, so you cannot follow that rule on the bottom, and that's very important to note. This is what matters. Make sure you don't do what's down here. Okay, so that being said, we move on and we can talk about some properties of the natural log of x. So we talked a little bit about logs before. You've had logs, I'm hoping, up to this point, but I'll do a quick review if you're not sure of logs. But we have the natural log, which we use, as you know, last time. We use that natural log a lot. So this is probably your second easiest function that you have to take the derivative of. So a couple things. They're talking about the different forms of a log. Here's one form, here's the other form, and remember that they're the same thing. One's exponential, one's log form. Okay, so talking about domain range and all this stuff, here's just a little quick summary here. When you're dealing with two functions, they're inverses of each other, so they're mirror images over this line. They're symmetric with respect to the line y equals x. That's what all inverse functions are. Okay, so we'll get to how these look here. If you have a natural log, so the first rule is x can only be positive. So you look at this little graph right here, every log function, this red one right here, every log function, the domain has to be greater than or greater than 0 for the x. You can't have anything negative. You can't even plug in 0. If If you try to plug in a 0 into a log function in your calculator, you'll see an error. If you try to plug in a negative number into a log function, you'll get an error. So that's what this x greater than 0 is. But here's the nice part here. Now, they're going to go through the entire long process of how to find the derivative. Remember, by definition. Remember that whole limit as h approaches 0 of f of x plus h minus f of x, all that stuff right there. So that's what they're doing. They're breaking this down into the steps that we first use how to find a formula. And you can always revert back to this when you start getting unique functions. Okay, all we knew up till today was the shortcut where we find the derivative of any x to any power. So they're going to find all these things right here, and then you find f of x plus h minus f of x. You get all of this, and a little bit of algebra here. You can pull out the h, or you put the h out, the 1 over h out in front, and then you follow the rules of what logs are, and you get all of this right here. Okay, and what matters is, at the end, you're taking the limit as h approaches 0. So like I said, I'm not going to go through every bit of these slides because, bottom line, you don't have to know how to derive what the definition is of natural log of x. You just have to know what it is. And in the end, you get something real nice and neat, and it's this right here. Okay? So shortcut is, if you are finding the derivative of the natural log of x, it is simply going to be 1 over x. That's it. That's all you have to remember out of this. That's all that matters. Okay? So that's it. I'll say that's it. That's the 2 things I want you to know from the get-go. And there's going to be a couple others, but these are the core ones here. All right? So this is an example. We're going to find the derivative of this function. And notice it's got the e to the x. It's got the natural log of x. So treat them as 2 individual terms, which they are. So it's 2 different derivatives. Okay? So the derivative of the first one, remember, if you take the derivative of e to the x, it is simply e to the x. A coefficient of 3 in front of it doesn't change anything. It's just 3 to the e to the x. The other case, the 5 stays there, and the derivative of natural log of x is 1 over x. That's where they get the 5 over x from. Okay, another example here. Find the derivative of this function, x to the 4th minus natural log of x to the 4th. Now the first thing is, remember, we learned how to find the derivative of the natural log of x. We didn't learn how to find it if it's got an x to the 4th or any other numbers in there, so you cannot have anything except for a natural log of x. That's all that we're knowing, that right there. So right now, this 4 is sort of messing up our universe. I can find the derivative of the first piece, but the second piece is going to be a little bit of work. So, got to remember some log properties. We have lots of properties in your logs, and if you remember, if you have a power on the item inside of a log, you can put it out front. So that's what happened to this 4 right here. It became that 4 out front. So now we're just dealing with x to the 4th minus 4 natural log of x, and now hopefully it's an easy derivative problem. And that's going to be the case in a lot of things we do here where, I've said this before, the derivative is not going to be the difficult step. It's getting your problem set up, and you have to do some rearranging and some equivalencies to make it ready to do the derivative. And then once you have it, like we have this form, now you do the derivative. So y prime, start with the x to the 4th. Derivative of that is 4x to the 3rd. We knew that one. And then the negative 4 natural log of x, just remember, the number doesn't matter. That sticks around. The negative 4, the coefficient, it's what is the derivative of ln x, and that is 1 over x, and that's where we get the 4 over x from. Okay? So that's how you calculate these, and like I said, it's a lot of preliminary work. It's getting the problem ready, and then the derivative is easy once you can get it in the right format, and you can apply what you know, apply your formulas. Okay, so a lot of times you're going to see here that they mention that the e is the preferred base. It's not everybody loves that. I will say natural log of e is, again, it's log base e. A lot of people like log base 10 or log base something because they can understand it better. But most of our problems are going to have that log base e, the natural log. So just kind of be ready for that. That's what they're pointing out here. Okay, so some other things here. Base should be always greater than 0. base is not supposed to be equal to 1, because if you have a base of 1, there's kind of an unlimited number of answers, or it's impossible. It's one or the other here. So exponential form and the first form you see is log form here. This is a very important thing. You have to be able to switch forms. Okay, so if you have y equals log base b of x, you have to remember what the definition of a log is. So what I always tell students when I first teach logs is log is always equal to a power. Okay, so whatever the log is equal to, they're asking for a power of something. Specifically, it's a power you put on top of the base. So you look in that first example right there, that equation, y equals log base b of x. Well, the log is equal to y, so that y right there is the power. What do you do with that power? You stick it on the little b. That's how they got this right here. And then that's what's equal to the last piece, which is just the x. So in a case like this, you have log base, or sorry, going back to here, the far right. They took the natural log of both sides, which we talked about in the last couple sections, where you can natural log both sides, perfectly allowed. And then what that gives you is, bring the y out front, another property like we just did earlier, that same property. Pull that power, that y out in front, and then you solve for it, and you get 1 over log b, natural log of x, and that's what log base b of x is. And you may remember that before, there was this change of base formula, where it said if you have any log of any base, you could change the base to, say, this a right here, by simply doing this. You take the old base and you stick it in the bottom, and then you rewrite it as 2 logs, both with the new base. So you can make that log. A could be 10, A could be 5. You can make any base you want. In this case, this is the log base e. They just chose that to be an e right there. So it's kind of, again, deriving a formula that you should have seen at some point, the change of base formula. And if anything, it's just reminding you and showing you, though, why it's true, why it happens. Okay, so they want us to find a relationship between b to the x and e to the x for any base b such that the base is greater than 0. So we have a function right here, and again, we're going to natural log both sides of it, and then they're going to bring that x out in front, and then they're going to solve for y. Okay, now make sure you're clear how that worked. It looks kind of awkward, where they got this from, but what happened is you can take the natural log of both sides, just like you can take an e and you can stick it to both sides here. But more specifically, let me go back one step. If you look at what we have right here, this is the same as log base e of y, this thing right here. Okay, so it equals all of this, and then remember the rules for between log form and exponential form. I can take this e, this whole log, remember, equals a power. So treat this whole thing like it's a power of that e. And that's how they ended up with this right here. That's how they got this part right here. They just moved it all over, and we get the y equals e to the x natural log of b. So like I said, sometimes these slides skip a step, or they just assume that everybody knows it. That's where that came from. So again, if you need to go back and rewind this a couple seconds and pause it just to see what I did there, so you can see how they ended up with this step right here. Okay, so you see here, then they talk about the derivative of the function e c to the x is c e to the cx. Okay, now this is a step that's, I don't like how they put it in here, I'll be honest with you. We're going to learn this in our next section coming up, so you can kind of take this for a word going on of what's happening. But for now, I'm going to go along with it and believe it. And what comes to matter is this fact right here. All right, if you have a derivative of e to the x, it's just plain e to the x. If you have anything other than e, like say 3 to the x, and you want to take the derivative of that, that's what this formula is right here, where it's similar to the e to the x. If I take the derivative of 3 to the x, okay, it's similar of e to the x in the fact that you get the 3 to the x in your answer, but because it's not an e, it's not exactly this, you have a little compensation here where all you have to do is multiply this answer by the natural log of whatever this base is. So that's another formula I want you guys to see, is that if you're taking the derivative of anything to the x, so e to the x, easy, 3 to the x, 5 to the x, 9 to the x, the answer is still that thing to the x, but you just have to multiply it by the natural log of whatever that base is. So that's the general rule. So like I said, a lot of the slides here today are just showing you how they get these formulas. I'm going to tell you, I just want you to know how to know what the answer is, not how do we get it. Okay, so this is one that we had earlier, this e to the x, and then we also learned this earlier today, this one right here. The derivative of natural log of x is 1 over x. So that's if it's a natural log, if it's a base e. If you have any other base, like this right here, the answer is still going to be 1 over x, just like we have here, but your compensation is you have to put this 1 over natural log of whatever this is. Okay, so I'm going to refer back to this formula page here, this slide, whatever number this slide this is, slide 13. We're going to go back to this a number of times just to back and forth when we do the examples later in this, and then when we do the homework. So these are the 4 that you have to know for this particular homework right now. Okay, so more examples. We want to find the derivative of part A, which is f of x equals log base 5 of x. So remember, if that's natural log of x, it's just 1 over x. If it's any other log, like this case, a different base, a 5, then the answer is still going to be 1 over x, but remember, we have to divide by or take a 1 over natural log of that other base, whatever that oddball base is. Okay, so like I said, if this was log of base e, that was natural log of x, which is log base e of x, the derivative of that is just 1 over x. But if you have any other base, in this case a base 5, the answer is still going to be the reciprocal of this x. Still going to be the reciprocal of that, 1 over x, except you also have the 1 over natural log of whatever this number is right here. Okay, so again, we're going to keep doing examples of these. On the second case over here, same thing. Remember, if it's e to the x and you want to find the derivative, the answer is just e to the x. Well, if it's 2 to the x and 3 to the x, it's still going to be a 2 to the x and a 3 to the x, but you have to multiply both of them by that base, that 2. So that's your compensation, steps. That's what you have to do whenever you're dealing with any of these. Okay, now we get to an example, a little word problem here. We have an online store selling guitar strings, X sets of strings, and the price is P for each set. And then they talk about the price demand. All right, so depending on, again, as X goes higher, you're going to get, a different, if you sell more, you get X, you get the P. They're inverses, they just relate to each other. Let me just say it easily. So if if you're going to sell a certain number, it'll be corresponding to a certain price. If you have the price set at a certain number, you're going to have a certain demand. And that kind of works the same. Just stop for a second and think in real life here. As your price is higher, what's that going to do? How's that going to affect the demand? As the demand is higher, how's that going to affect the price? As your price gets lower, well, maybe not everybody wants them, etc. So that's what this formula is, this equation that, again, we'll get to more how in a bit. But right now, let's just say that's what the price is. We want to know how to work with it. So they're asking, given this equation right here, find the rate of change of the price with respect to demand when the demand is 100. So remember a couple things. Rate of change is like a slope, okay? It's a relation. And remember, the slope always means derivative. When you're looking for the slope of the tangent line or how much something is increasing, that's the rate of change. The instantaneous change, that's the derivative. All these things mean derivative. So what we have to do is we need to take the derivative of, that whole function, not just that right there. That's our first step, is take that derivative. Well, now we have the tools to find the derivative. We're going to find the derivative of P in respect to X. So remember how this works. You still have your 12.5 in front. The derivative of anything to the X, okay? If it's e to the X, it's just that. If it's anything else other than e, in this case 0.998, the answer is 0.998x, but you also have to multiply it by the natural log of that base. that 0.998. That's your derivative. So then at this point, they want to know what go back. This formula tells you your rate of change at any point in time. And as we saw from curves of lines, the slope varies depending on where we are. We need to know what the x is. So they tell us, we have the x. Sorry, accidentally hit a button. So we have the x at 100. Our job is, once we find the derivative, let's just go plug in that x. And that's what we're doing right here. So you see, when x is 100, they take that same derivative we just found, they replace the x with 100, and then plug all this into your calculator. Now, like always, no disagreement, or we understand completely how to plug this into a calculator. Pull out the calculator and just make sure we see this. Now, I start with this. It doesn't make a difference which one you do. In this case, I'm going to find the 0.998 to the 100th power. So we talked about this before too. Here's your power button. I hit the 100, and then I multiply that by 12.5. And then I'm going to multiply it by this 0.998, the natural log of it. And the nice thing is I can push 0.998 and I hit the natural log. And notice the moment you hit natural log, this is showing the natural log of 0.998. I haven't finished the problem because I still have to hit the equals, and that's how I end up with this one right here, the negative 0.0205. That's how you see where they got this number from. Okay, so what it's saying is, when you get to 100 sold 100 sets, the price and the demand, it's starting to decrease by about, you see, 0.02, that's talking dollars, about 2 cents per set when we're selling that many. Okay, the demand's starting to go down when you start selling that many. So that's all that's happening here in this problem, that example. That's how they're getting that one. So let's go to another one here. We have another one of these continuous compound interest. Remember the PERT formula that we had before? So they're saying right here, an investment of $10,000, that's the principal, the capital P, earns an interest rate of 4%. Remember, R is 0.04. We want to find the instantaneous rate of change. So once you see instantaneous rate of change, you think, I need to get the derivative. So right here, okay, what they didn't show was that formula, A equals principal E to the power of RT. Okay, so in our problem here, where are we at here? We're plugging in the 10,000 right here. We're plugging in the rate, which is the 0.04. That's how they got this. Okay, so now there's a derivative, and like I said, I don't care for this next part because it's not exactly clear. And the good news is you're not going to see this directly on this homework, but I'll just talk about it here. What happens is when you take the derivative, if I ask you to find the derivative of e to the t, the derivative of that is just, again, e to the t. Well, we've got this number out in front. So the rule is, we're going to learn this next video, next section. There's something called the chain rule. You're supposed to also multiply this out front. That's where they got the 400. Now, like I said, it's kind of early in my mind. I kind of feel like next time I teach this, I'm going to do 2.3, then 2.2. Or sorry, 3.3, then 3.2. But it is what it is. It's here. And this is just kind of, for this problem, take my word, this is the derivative, and you'll see it more, like I said, in section 3.3. And again, this example, kind of out of place. It's not really going to be here for your homework anyway. But what I want you to see is once you have the derivative, now we can plug in the 2 for the 2 years to see what the rate of change was. So you plug this in, you get 0.08, find e to that, whatever it is, multiply it by 400, and we get the 443, which is saying that after 2 years, you're growing at a rate of about $433.31 per year. So again, instantaneous rate of change. That's what the derivative is. Okay, so I'll skip the next one because it's the same kind of thing. Like I said, it doesn't really hit your homework right here, but this one will. All right, we have a model for growth of a sandwich shop franchise that is n of t equals negative 765 plus 482 natural log of t. And we have n of t is the number of locations, and the year 0 represents the year 1980. Okay, so just to make sure we're clear on this one, 0 is 1980. Pretend that's when the shop was founded. When it's 1981, t is 1. When it's 1990, t is 10. Here, we're in the year 2022, so that's going to be t is 42. It's how many years past 1980 is your t. So they want you to estimate the number of locations in 2028. So notice, I didn't see instantaneous rate of change or anything like that. I'm just asking straight up, what's the number of locations? So n is the number of locations, t is the year. We're going to just plug in this case, 48 into the example. So you see how they talk about that? 2028 is the year t equals 48. And no derivative, we just plug 48 right in this formula, and we get 1,101. So take the natural log of 48, multiply that by 482, subtract the 765, and that's how they arrive at this answer. Okay, so that one's fairly good on your calculator, but that's just talking about how you still realize you're not always doing derivative. You have to stop and think about, what are they asking? If they ask for there's certain keywords that tell you, go get the derivative. Not always do you automatically get that. In this case, just go plug in t and get the value of capital N. Okay, so now we have the same, I believe it's the same equation. Yeah, negative 765 plus 42 natural log of t, same thing, okay? Now they want to know rate of change. So again, that's your indicator. That's the phrase that says go get the derivative. Whereas in this last problem, there is no mention of that. That's why we didn't get the derivative. We just went and found what the answer was, the number of shops. So now, 2028 still is 48, but we have to go find the derivative. Now, they jump right to the derivative, but we know this. Go back up here. When you find the derivative of this equation, the derivative of negative 765 is 0. Remember, the derivative of a constant is nothing. That disappears. The derivative of natural log t, that's our new one of this day. It's 1 over t. That's where they get this 48 times 1 over t from. Or in this case, 482 over t. That's the derivative. That's what tells us the formula to tell the rate of change. So that's why we found the derivative, because it said rate of change. Now we're going to plug in the 48 to that new formula right here. And you see we get a little more than 10, but it's telling us that in the year 2028, we'll be growing at a rate of about 10 shops per year. Okay, yeah, 10 shops. So that's what the conclusion is then. And the interpretation here, this interpret the results, this is important. I don't want you guys just to become robots where you see this, you did that. I want you to understand what the derivatives always mean. Remember, their rate of change. They're telling you how fast the graph, in this case, the sandwich graph, or the shop graph, how much your shops are either increasing or decreasing. We want to know with the derivative, how fast is it growing? Or is it decreasing, and at what rate? That's what's going on here. So whenever you find the derivative, it's telling you how many, and in this case, what's the rate the sandwich shops are either growing or decreasing each year, and that's what the derivative told us when you plugged in the 48. If I plugged in a different number, of course, it's going to be a different result here, because they're growing at, they're going to start slowing down as kind of the idea as time goes on. Kind of like a good example, think of a Starbucks franchise. Okay, if you've been around long enough, you saw it started out and then they just started growing and growing and growing, hundreds, thousands a year across the world. But you look at it now, they're probably, I know they've had a lot of closures aside from the pandemic, but if they followed a similar model, you'll see that after so many years, they really can't add too many more. They add a few here and there, but the growth starts dropping tremendously. And like I said, in this case, sometimes we go negative, but this is how we model it. This is how we can see what. Okay, so that's it for the lecture. Like I said, there's not a whole lot of stuff that matters. It's those 4 formulas, and I'm going to pull these up, kind of our little cheat sheet that I want you guys to have right here. We're going to use this all the time. Not all the time, but for this particular section of homework, this section 3.2, we're going to use this a lot. So I'm going to keep referring back to that. All right, so entering our course, just kind of catch up where we are here. We're in the 6th week. This is the first half of homework number 6. So let's get in our assignments. And homework number 7, I'm sorry. 7th week, it's going by fast. So, homework 7 is where we are, and we see we have a lot of problems here, but let's start to see what we get here out of section 3.2. Okay, now the good news is, bad news, a lot of problems. Good news is, some of these problems are fairly fast. There's not going to be a ton of work that you have to do, not a lot of writing. And a lot of these early ones are just kind of hoping, to refresh your memory of what it means when you're solving for a log. So as you heard me earlier, when I'm talking about a log is always equal to a power. Okay? Every time it's a power. So when I see a log equal to something, I know it's a power. This log equals this power. So when I look at this, I see my power is -4. Well, my base is 2, so I put that power on there, and it equals to whatever's left, in this case, the thing inside the log, which is x. So that's what I have to do to solve. I'm just converting forms from log form to exponential form. Then, of course, you have to remember what that means, and that should mean 1/16 is equal to x. And that's all we have to do on this problem. Okay? So now, moving on, like always, I'll just kind of go by 4s here and see what we get. So we did number 3. Let's check out what number 7 is all about. In this case, they want you to use your log properties. So there's a lot of properties. If you need to go review, there's going to be stuff in your ebook here. I'll go over a few. I've already talked about a couple. One of them is that, remember, if you have a log and you're adding it with another log, as long as you have the same base, you can combine them into a single log where you multiply your answer together. Okay, if these logs were subtracting, then that answer on the right would be x over y. But what I want you to see is this goes the other way as well. When I have natural log of x times y, notice a natural log is still a log. It's a log base e. I can split that into 2 pieces. So when I have natural log of x times y, I can split that into natural log of x plus natural log of y. It's the same formula. It's just reversing a little bit. And that's the unique thing about log properties is they go both directions. Okay, it's not just one-way formulas. These formulas, you're going to have some cases where you go left to right, some cases when you go right to left. And it's important because just like switching from log form to exponential form, you have to be able to know how to convert anything, because sometimes you're at a stage of a problem where you just can't get the answer. And how do we get out of it? Let's try switching forms. I'm stuck. Let's go from log to exponential form, or go from exponential to log form. Or in this case, I've got a log that's kind of complicated. I want to split it up a little bit. And when they say simpler, and that's kind of a loaded word, I'll say that. A simpler form in this case, they're trying to get the inside of the log to be simpler. So yeah, I have 2 logs, so it looks like it's worse. It looks like it's double complicated here. But what's nice is what's inside each log is just a single variable now instead of 2 pieces. That's why it's considered simplified. Okay, so let's look at number 11. Same kind of type problems. And again, they'll ramp them up. The first dozen or so are going to be this way. Then we start getting into these derivatives here. Okay, so we have f of x equals the natural log of x plus 6e to the x minus 5x squared. So they want us to find the derivative, and you just have to remember all the rules. Okay, so I'll kind of throw that on the screen real quick to remind us. Remember, when you have an e to the x, the derivative is just e to the x. That'll take care of this, and the 6 just attaches at the front. This one on the right is an old problem. We've done that before where it's a regular x base with a number power, and we bring the number out in front, and we decrease the power by 1. And then the third piece, this first one, is the natural log, which is this one down here, which says, give me the reciprocal of whatever is inside that natural log. So you treat this like 3 individual problems. That's the derivative of natural log of x. This is the derivative of 6e to the x. Basically, it's a copy of itself. And the last one, bring the 2 out front, so 5 times 2 is 10. Drop the power from 2 down to 1, and that is it. That's all we have to plug in here on this problem. Okay, so I'll type the 1 over x plus 6e to the x minus 10x, and there's our answer here. So as you start getting more complicated, again, like always, feel free to pause this, look at what I've done, and then once you're good, unpause it and go on to the next one. So we'll go to number 15 here. Okay, so in here, nothing much different. We have f of x equals 7 e to the x minus 9 e to the x. Or sorry, the first one is x to the e. I read that wrong. The second one's e to the x. And I love this problem because this really makes you stop and think about how this works, to see the difference of the two. Okay, so notice, and this is it's a trick problem because it's one that's meant to catch people. I'll tell you right now, don't write this, but just watch. This is what I see all the time. The derivative is the same thing, okay? Now, what I want you to see is, do you see the error? This part is good. That's exactly what it's supposed to be. And again, I'll show you our little cheat sheet here. Remember, the derivative of e to the x is e to the x. That's exactly what we have right here. On this other case, this is x to the e. That is not what this formula is. In fact, x to the e is exactly like what you've had before. Okay, so pause for a second. If I gave you 7x to the 11th and told you to find the derivative of this, you know the rules. Oops, not a negative. You know how to do that. We've done that before. That's used to be the easiest derivative. Remember, you bring the 11 out front and multiply, so you get a 77. Drop the power down by 1, you get a 10. That rule has never changed. You take that, and this works for any power. Notice the difference of these two. When it's a base e, we follow our new shortcut. When it's a base x, you follow your old way, like I demonstrated down here. So how do we do that on this one? It's a regular x. Remember, that's x to the second, third, fourth, fifth, any power of x, including decimals, fractions, negatives, or e's. So what do? For the derivative, you bring the e out front, you multiply it. Just like I multiplied this 11 over here times a 7, well, we multiply the e times a 7. And then the rule is, you still have the x there, just like I had right here, and you drop the power down by 1. Well, how do I drop an e by 1? Well, very simple. You just say e minus 1. Now in your calculator, you'll see that's 2.7 minus 1. It's like a 1.7. But because it goes on forever, we really don't want to write any more. We don't want to go to a decimal calculator because it doesn't say that. We're going to leave it exactly as we see it right here. That is it. That's as simplified as it's going to be. Okay? So type that in as the derivative. If I can, we get 7e ex to the power of e minus 1. That's the first term. Then minus 9e to the x, and there's our answer. So again, pause and check this out if you have to look at it a little bit longer. If not, resume, and we'll go on to number 16. And that's the key is, I said earlier I didn't want you to be robots, but you have to be in terms of don't let your heart make a decision here. When you're doing a derivative, you're following a formula, it's important to know what formula are you following, and then go about it that way. Go follow the steps of what it's supposed to be. Does it look like something you had before? So once again, that's what we know. If you see e to the x, it's e to the x. If you see this, it's 1 over x. You see one of these, it's that. If you see an x to a power, it's following the rules that you've already learned, the stuff that we've been doing for a couple of sections now, a couple of weeks now. Okay? So in this one, we have a student claims the line tangent to the graph f of x equals e to the x. So that's our graph. That's our function right here, this curved line right here. Okay? That's f of x equals e to the x. At x equals 2.5. So remember what this means is the tangent line. There's a bunch of lines tangent to the graph, but they want the one right here at 2.5. Right there. That's the dot at 2.5, and that red line is where the line is tangent right there. Because if we're talking at other x's, you know, here's a different tangent line. Here's a different tangent line. There's all kinds of tangent lines, but that red one is the one that's hitting the graph right there when x equals 2.5. Okay, so what they're saying is that this red line, okay, so when they say the line that's tangent, I'm going to circle it right here. That line they're talking about is the red line. That's why I outlined it in red. She is saying that it runs through the point 1.5 comma 0. Now, I kind of eyeball it, and then let me blow up this graph a little bit. Okay, well, that didn't do a lot, but oh, let's try this. Okay, so by eyeballing it, it does look like this red one does hit the point 1.5 comma 0. It definitely appears that way, but the question is it so? Is it for sure? How do we prove it? Because the graph looks like it. Now, if you're using a graphing calculator, yeah, you can prove that, but we want to prove it algebraically or with our calculus here. How do we prove that that tangent line is there? So think about how this works, okay? To get, at x equals 2.5. Okay, so first we want to get an equation of this red line. So we've done this before. To get an equation of a line, we always need a point and we need the slope. Well, I know a little bit. All I know is it's tangent, and I know the x is this. So I know there's kind of a point, 2.5 comma something, but I don't know what that point is. All right? So I'll come back to that. We also need to know what the slope is. I don't know that, but I do know how to get the slope because remember, if I can take the derivative of this, which is f prime of x, we get that. If I plug this right here, this is the derivative. This is the formula to tell us the slope of every one of these tangent lines over here. Every one of them. And all you have to do is you plug in a particular point, in this case 2.5, and that's going to tell us the slope at that spot. So this right here, and I can plug it into a calculator, but I'm just going to leave it there for a second. That is the slope of that red line. Okay, we know that because it's tangent. The derivative tells us the formula for the tangent lines. You plug in the corresponding x where it's touching, which is 2.5. Whatever you get, e to the 2.5 in this case, that is the slope of our red line. So think about it. We know this, and we know part of a coordinate. Well, how do I find the other coordinate? Remember, the other half of this point right here. Remember, it's on the function right here. So if I plug it back into the original function, I'm going to get the y value. I'm going to get the other part. And coincidentally, it is e to the 2.5. Okay, that's the coordinate right here. All right, now if it's bothering some of you like, well, I don't know what this means here, let me just show you. 2.5. Okay, 2.5. That's the power of e. So I hit that e to the x button, we get 12.182. So you see right here, that coordinate is at 2.5 comma 12.2. That's where it's hitting. So you look at the graph right here, it's hitting right there. And it also happens to be that that slope is 12.2. Now you may not see it's a slope of 12.2. It doesn't look like it's rising that much, but remember the scale is not quite correct. See how they're counting by fives here? These are counting by half. So it's not a correct scale, but if you were to scale this correctly, it would in fact be a slope. It would definitely be a slope that's going up by 12, okay, for that red line. So here's how we do this now. Remember our good old formula, y minus y1 equals m times x minus x1. So I plug in the e to the 2.5. I plug in the e to the 2.5, x minus 2.5. And I'm going to work with this equation right here. Okay, so I'm going to move this out of the way for a second just so we can have more space to write. And my goal right now is I want to get the equation. Okay, so we get y minus e to the 2.5. equals e to the 2.5x minus 2.5. I'm sorry, there's supposed to be an x lower, not in the power. I'm distributing that e to the 2.5. So this right here is distributing to here and to here. So that gives me e to the 2.5 times x minus 2.5e to the 2.5. So I get e to the 2.5x minus 2.5 e to the 2.5 plus e to the 2.5. Now this last part's going to be kind of fun, and I say that sarcastically. You look at these two terms here on the right, this one and this one, they're both e to the 2.5. Well, there's one of them, there's negative 2.5 of them. Together, because they're exactly the same, it's a negative 1.5 e to the 2.5. So this is the equation of that red line. Okay, that line that I just talked about, that red one, that's the equation of it right here. So the question that they were asking on this problem was, is this point 1.5, 0 a point that runs through this red line? So I'm just going to move up top here. We saw by that picture, it sure looks like it does, but I'm not too sure. But here's what we can do. We're testing 1.5, 0. All right. Is that actually a coordinate? Well, I'm replacing x with 1.5. And notice I have a 1.5 e to the 2.5, a minus 1.5 e to the 2.5. We sure in fact get a 0. We confirm that yes, that point's good. Okay? So it was a lot of algebra, a lot of steps to show that, but that was our conclusion. That's what we're trying to figure out here. So let me just plug that in here. So is the student saying that that passes through the point? I'll say yes. Got that one. And then there's a second part. Okay, so let me go back. Okay, I'm going to let you pause if you need to see this, and I'm going to clear off the screen a little bit, a lot. Okay, let's pick back up where we were. So part 2 is asking, will the line tangent at 3.5 pass through the point 2.5, 0? Okay, so this is basically the same problem. We want to change this to be x equals 3.5. So it's the same thing. Now remember, I'll remember from earlier, the derivative was this. Okay, therefore the slope of that new tangent line at 3.5 is e 3.5. That's the new slope. And it makes sense because as you go a little further, 3.5 is right around here. Notice the tangent line is going to be a little steeper. So that's why you have a steeper slope right here. Now my point is going to be the point of that new line, this black line, for example. Remember, it's touching our graph at 3.5. So it's going to be 3.5 comma e to the 3.5. So the question is, does the point 2.5 0 pass through there? Okay, so I'm going to do the same thing I did earlier here, and I'm going to try something a little bit different now. Just an alternate way, and maybe you've noticed this, maybe you'll like this better, maybe you'll hate it, you go back to the first way. So they're wondering, is the point 2.5, 0 I can draw this right there. Is that on the line? Well, think about this. We know the slope, right? We know one point, and we're wondering about a second point right here. So think about this. If those 2 points are in fact on that line, we know one of them is. If this new point, this point number 2, if it's on there, they are going to have that same slope. So I'll do this problem a little differently where we have m, back to our slope formula, good old y2 minus y1 over x2 minus x1, just to see if in fact it matches and we get the same slope. So it's basically what we did a second ago on the last part, but we're going to do, I'm hoping to save a couple steps. So we know we have the slope, which is e to the 3.5. We have y2, which is 0 minus y1, which is e to the 3.5. On the bottom, we have 2.5 minus 3.5. And you might see where this is going. If not, I'll keep doing this. On top, we have negative e to the 3.5. On the bottom, we get negative 1. And sure enough, those negatives cancel, and we get 3.5. E to the 3.5 equals 3 to e to the 3.5, sorry. Therefore, I'll just plug this in and verify that that looks good as well. Okay, and they're asking here, will it pass through there? So, yes, it will pass through the point because the tangent line is, looks like it's the same as that line right there. Passes through 2.50 and 3.5, f of 3.5, yes. So that's what we get, and there's our answer there. So let me, again, let you pause. I'll try to keep the answer clear here on the bottom so you can see it. And then let's try this. Okay, I was trying to get it where you can just see the answer and see the work. So you can kind of pause this because I know everything's sort of butting against everything else. Okay, a little bit more, we'll get it. Okay, so there's your answer. Pause it if you need to look at it, and then we'll go on to the next one here. So let's look at number 23. Okay, so now we want to find the derivative of dy dx, find dy dx of the equation y equals 8 log base 6 of x. Okay, so again, in the beginning, don't be afraid to do what I'm doing here, where you take this sheet. Hopefully you have this written down already, but I'm going to look at these formulas and I'm going to use these to get our answer. So notice when I'm doing a derivative, I don't care about the front number. The 8 doesn't matter. This constant just follows along. What matters is how do you find the derivative of the log of 6 of x. That's going to refer to this formula right down here. So the derivative of this, the 8 stays there. It's going to be 1 over the natural log of that base, which is 6, times the 1 over x, and there's our answer. Okay, now I'm going to clean it up a little bit. So first let me get rid of this. Since we used our formula, we have it. Now we just want to clean this up a bit. There's not a lot I can do, but I will try to make it a little bit better. Let's call it 8 over x natural log of 6 should be good. Okay, the 8's on top. The 1 over x is for the bottom. So when I plug this in, it should be good. We're good there. So again, pause this if you need to see. Then we'll move on. Let's look at number 27. Okay, so 27 says use graphical approximation methods. So when you see that, what does that mean? That means get your graphing calculator out or go to Desmos like I'm doing right here and see how to do this. They want you to use the graphing tool, the technology on this one. So they want us to find the intersection points of these two graphs. We have two functions. So like I said, you can try to graph these on your own, but this is literally an exercise of can you use the graphing calculator to do this. So you can use your own or you can use Desmos like I said, and I'm just going to use this one right here, use Desmos. So the idea is type it as close to what you can on that one and it should work. We have natural log of x squared. Okay, so this is what the function is, and don't be afraid to pull it out, zoom in, zoom out, just so you get a better feel of how this graph looks. And then on the second line, I'm going to do the g of x equal to 7x, and hopefully you remember that's just going to be a line that's got kind of an upward trajectory, a high slope. So here's the functions, and what we care about is where they intersect. So graph right there. We have this coordinate, and like I said, you can go around, but I'm just going back and forth. You see how it's showing the values of the red line, and I'm showing these, and if I want to know the one that's there, I just hover over it, and I get 0.26 and 1.18. Make sure I get that. Yeah, 1.818. Okay, so the intersection points are ordered pair 0.26, and then make sure you answer this part. Round it to 2 decimal places. So 0.26. You don't have to put the 0. I just like to do that. 1.82. Because remember, we're going to round this to 2 decimal places so that hundredths place, that 1.81 becomes a 1.82. And hopefully good. Oh, what did they say? They don't like this one. Ordered pair, decimals rounded to 2 decimal places, use the comma. Oh, I forgot to close my parenthesis. One little thing, and you see it's wrong. So be aware. That's why I always try to do this. It's good that I get marked wrong on some of these, so you kind of see that we had the right answer, but that one little lack of a parenthesis. If this is a real life test, yeah, I'm going to give you credit if you forgot it, even though you shouldn't. But the system's very finicky at times. You have to make sure it's got the ordered pair. It's got both parentheses. Okay, so that's it for number 27. Let's look at number 31. I believe. See here. Okay. Formula for a relationship between weight and blood pressure in children is given by P equals 11.2 times parenthesis 4 plus natural log of x. And x has got to be between 10 and 100. And P is measured in millimeters of mercury. And x is measured in pounds. Okay, so you see what they're talking about. Your pressure is going to be this millimeters of mercury. So whatever P is, it's that many millimeters, and X is the number of pounds of the person. So find the weight at which the rate of change of blood pressure with respect to weight is 0.6 millimeters of mercury. So remember, rate of change right here, that's going to tell you one thing and one thing only. Go find the derivative of this function. Okay, so before I find the derivative, I like to distribute to get all this fixed up a little bit better. So I distribute the 11.2. So that multiplies by 4, we get a 44.8. Then we have the 11.2 natural log of x right here. Now I find the derivative. Derivative of a constant is nothing. Derivative of natural log of x is 1 over x, so this just becomes 11.2 over x. That's my derivative of the blood pressure, so it's the rate of change of the blood pressure. Okay, so this is blood pressure. This is rate of change of the blood pressure. So always make sure you understand what you have, because you're going to get 2, 3 functions. Each has their own derivative. You got to know what every one of them stands for. All right, so now they're saying find the weight. So remember, x is the weight. That's this one right here. That's the weight. They want you to find the weight where the rate of change is 0.6. So it's kind of asking it weird. What they're saying is they're giving you the rate of change. They're telling you that's 0.6. So that's how we get the 0.6 right there into that derivative formula. A lot of times you're going to go plug in an x and get the derivative, get the value of the rate of change, but this one's a little backwards. They give us the rate of change, so that goes right there. And a way to make sure is, remember, a lot of people would do this. They literally would put the 0.6 right here because that's what you're used to, because it makes sense. When you do that, just always remember, what's x stand for? X right here is the pounds, is the weight. They said it somewhere. Yeah, it's pounds. It's the weight. So when you're plugging in 0.6, you got to ask yourself, is that the weight? No, that's the millimeters of mercury. It's got to be on this side over here. So now we multiply both sides by x. Then we divide both sides by the 0.6. And we get x equals 11.2 over 0.6. And we're going to get the decimal for that. And they say round to the nearest pound, so when I get the calculator out, I'm going to get a long decimal. I just got to remember to round that thing to the nearest whole number, the nearest pound. So 11.2 divided by 0.6 gives us 18, and a bunch of sixes that go on forever. Rounding to the nearest, that's going to round it to 19. Okay, so that's what I'm putting in right here. And that's it for number 31. So let me go back again. If you need to pause and look at the whole thing, go ahead. Not, go ahead and unpause, and we're back to where we need to be. Let's look at number 35 now. So you see there's a lot of homework problems here, but they're not as ugly. They don't take as long. So in this one here, this is now we're in section 3.3. So this is, you know, we're done with the 3.2 homework for now. So I'll stop right there, and that should allow you to get through at least half or good. You should get through about 32, 33, 34, somewhere around there. Now there's a lot of problems here, but again, on the next homework, these are going to go a little quicker. So maybe it'll take a couple more minutes for me to work all these out in our next video, but for now, this is what you need for section 3.2. You should be good. I'll post another one on 3.2 as soon as I can. And if you have any questions, like always, shoot me an email. And of course, a reminder of quiz number 6, I believe, is what's due Monday night. So make sure you get that in. If you have, if you haven't gotten it, make sure you get it in there and then start working on our new stuff here. So as you can see right here, quiz 6 due Monday night. Okay? So again, any questions, let me know. If not, have a good one. We'll talk to you next time.